Observatory's Living Room Lecture Series. If you've been joining us for all of our events, the Friend of Lick Observatory FOLO Family Dinner, our Ask an Astronomer event, and of course, these living room lectures, you will have heard from our UCO leadership. You will have heard from some of our resident astronomers at Lick Observatory, and both supernova hunters as well as our exoplanet hunters. This week, I'm delighted to introduce one of our black hole hunters. Joining us live from her living room in Southern California, where she will be trying to keep the rest of her family outside of the living room like the rest of us, is Dr. Andrea Ghez. As you all know, Andrea is an expert on the supermassive black hole and the center of our galaxy. So I expect that we'll be hearing about that in addition to some other topics this evening. She's been featured on BBC, the Discovery Channel, the History Channel, so much more. And tonight, we're so thankful, Andrea, that you are talking to us directly.
I'm so pleased to have the opportunity to do one of these virtual talks and to reach an audience that I wouldn't ordinarily have the opportunity to do so easily. This is actually my first virtual talk. I've attended many, but this is the first that I'll be doing as a public talk. The talk that I'll present to you this evening is an overview of the work that I've been doing at Keck Observatory for the last 25 years. We're just in the month where we're actually celebrating our 25th anniversary of the inception of this project. So this is actually a particularly exciting time to be thinking about and reflecting upon both what we've done over the last 25 years and how we're moving forward. Now, hopefully you're seeing my screen now. So I'm the director and the founder of UCLA's Galactic Center Group. I began this when I first joined the faculty at UCLA. And UCLA is one of the campuses that make up UC Observatories that's headquartered at Santa Cruz. So I've been fortunate enough to have both access to this facility and to be one of the people who've been involved in the development of this facility's capabilities, and in particular in our ability to get very high angular resolution images. So these are projects that are done in collaboration across the UC system and in partnership with our partners at Caltech and Keck Observatory. So the Galactic Center, what we call Orbits Initiative, because we have the objective of this project has been to measure the orbits of stars at the center of the galaxy, is to transform our understanding of black holes and their roles that they play in the formation and evolution of galaxies, to push on the technology, because as you'll hear in today's talk, this is as much a story about science as it is a story about technology. So the way I think about the work that my group has done is it's really technology-enabled discovery. It's discovery that's enabled by tremendous, huge leaps and bounds in our ability to see and measure what's going on in the universe. And in our group has also done a tremendous amount of education and outreach. We focus both in training students in this new technology, as well as focus on diversifying the workforce. This is a topic that I've been passionate about for years, given the low numbers of women in the physical sciences. And astronomy has just the wonderful ability to excite the general public about science and technology. So we're very committed to that piece of outreach. Okay, so let me start with a question that I love to drive this whole project with, which is, how do you observe something you can't see? And this is an essential question if you want to find and study black holes, because black holes are objects whose black holes are objects by definition that don't emit any light, so that we can't see them directly. But we do have a way of finding them, and that's what I'll discuss this evening. So we can not only find them, but we now have the best example to date for the existence of these supermassive black holes, and I'll get to what I mean by supermassive in a moment, at the center of our own galaxy. And we're now using the center of our galaxy, as a laboratory for understanding the physics of black holes, as well as understanding the astrophysical role that they play in the formation and evolution of our galaxies, which are the building blocks of the universe. Okay, so to begin with, let's agree on what a black hole is. In fact, it's one of the most exotic objects in the universe, so it seemed appropriate to start with a totally blank slide. So black holes are objects whose mass is confined to 0 volume. So in spite of the fact that we're going to talk about supermassive, which implies that they've got a tremendous amount of mass, they have no finite size. And in fact, what the reason that black holes are so compelling, both in terms of the professional setting as well as the amateur setting, is that they represent the frontier of our knowledge. They represent the breakdown of our understanding of how physics works at the interface between general relativity, which is what Einstein is so famous for, in terms of his models and understanding of how gravity works, and quantum mechanics, which is the study of very small things. So black holes are both very small and have tremendous gravitational fields. So despite the fact that they have no finite size, there is a size that we can associate with these objects, which is known as the Schwarzschild Radius. And the Schwarzschild Radius is important to us for a number of reasons. One is that if mass is inside its Schwarzschild Radius, and every object has a Schwarzschild Radius associated with it, at that point, all known forces are overcome by the force of gravity, which forces the objects to collapse to the infinitesimally small object of a black hole. So in other words, once you show that there's some mass inside the Schwarzschild radius, you have the proof of a black hole, and the object will become a black hole. So that's both in terms of physical process and proof. Now let's look at the size of these Schwarzschild radii. It's a very simple relationship. It depends only on mass. The more mass of the object, the larger the Schwarzschild radius. So if you were to take the Earth and squeeze it down to the size of a sugar cube, if there was some process that we could do that with, it would become a black hole. If you could take the sun and shrink it down, and I had to put this to UCLA's campus or any large college campus, it would become a black hole. So you see the more mass of the object, the larger the Schwarzschild radius. In fact, it's just a one-to-one correspondence. Now, today we think that astronomers and astrophysicists think about black holes in two very different settings, and they come about for two very different reasons. So the process by which you can get a large amount of mass inside of a small volume depends on the mass. So the first kind of black holes that were recognized were what we call, ordinary mass black holes, and these are the outcome of the most massive stars that we know about in our galaxy. These are stars that start their life off with more than roughly 30 times the mass of the sun, and at the end of their life, they explode and become the supernova. So it sounds like one of your earlier talks was about supernova. So supernovas are emit a tremendous amount of light from the explosion. So that's actually the outer layers of the star where gravity is actually losing, and the mass is going out into the universe. This is the picture we see, which is the remnant stuff. But in the inner layers, gravity wins, and gravity overcomes all other known forces at the center, forcing the center of this object to become a stellar mass black hole, so roughly 10 or so times the mass of the sun. What we're going to focus on today, or the ones I'm interested in, are the supermassive black holes. So rather than being roughly 10 times the mass of the sun, these are black holes that are 1 million to 1 billion times the mass of the sun. And the story here and the development of our understanding is very different. So in the first case, those objects were predicted from theory. In other words, we had a model for how stars evolved, and we predicted the existence of black holes, of the little black holes. In the case of the supermassive black holes, it has been a case where we've recognized observational hints that point us in the direction of much more massive objects that probably formed by a very different route. So observations came first rather than the theoretical model. In this picture, I'm showing you a picture taken with the Hubble Space Telescope. It's known as the Hubble Deep Field. It was taken in a direction that's outside the plane of the galaxy, so you can get a very deep picture of the universe. And every single object in this image, except for the one star with crosshairs here, is a galaxy. So these galaxies, each galaxy has roughly 100 billion stars in them. So the scale is very different than the one star that I was showing you earlier. Now, the question is, what gave rise to the idea that these galaxies harbor black holes at their centers? Because it's certainly not these pictures that are taken at optical wavelengths, which is what your eye detects. And the original notion that these galaxies might harbor supermassive black holes came from observations of active galactic nuclei, where the nuclei, or rather the center, seems to be producing a tremendous amount of energy. And you see this in two different ways. One is that there are jets of emission that are emanating out from the center, giving rise to these blobs, and we can measure how fast these things are moving on the plane of the sky. And there's a tremendous amount of energy in these jets. And also at the center, the emission at the very heart of the galaxy is unlike anything that stars produce. So it was posited that these galaxies, this unusual activity in these galaxies is driven by matter falling onto a very massive black hole. Okay, so, and these galaxies are a tiny fraction of the not a tiny, it's 10% of all galaxies. So these are thought to, in some sense, to be the prima donnas of the extragalactic world. And this led people to suggest roughly 50 years ago, do all galaxies harbor supermassive black holes? So even the galaxies that are quiet and have no signs of a big jet or an unusual emission at the center of the galaxy. This is a galaxy that looks very much like our own galaxy if we could get out and look back inward. So galaxies are, for the most part, flattened disk-like structures. In our galaxy, we have a configuration very much like this with the spiral arms. And our sun, and where we live, the Earth, is roughly halfway out from the center of the galaxy in one of these arms. So we have this unusual view back through the plane of the galaxy. So 50 years ago, we were asking, is it possible that all galaxies harbor supermassive black holes? And if you're going to suggest such a case, the idea would be that these are galaxies that are simply accreting very little matter. So the active galactic nuclei are the ones that are having a huge feast, you could say a Thanksgiving feast, and these little galaxies, like our own, are maybe just having a snack. So at the beginning of the project that we launched 25 years ago, this is when I first started my faculty position at UCLA, I was interested in demonstrating the existence of supermassive black holes. And if you could prove that, and our galaxy is certainly the best place to look if you believe that all galaxies harbor supermassive black holes. So our galaxy is an ordinary garden variety, nothing special about us galaxy. But it is special in the sense it's the closest example of the center of a galaxy that we'll ever have to study. The next closest galaxy is 100 times further away. So we have far less, so we have far more ability to see detail. Now, this is a picture, this is a beautiful picture taken by Brad Lewis on the flank of Mauna Kea, where you can see the plane of our galaxies. Just because we're in the middle of our galaxy, we look out and we see the plane. So the white stuff on either side of the dark streak in the middle is the starlight. And there's a dark streak because not only do we have a lot of stars in our galaxy, but we have a lot of dust. And dust is very good or very efficient at absorbing light whose wavelength is comparable to the size of the dust particle. So at optical wavelengths, it absorbs most of the light. 1 out of every, I think it's 30,000, actually, sorry, 10 to the 10 million photons, light packets that comes from the center of the galaxy is absorbed. Unlike in the infrared, or just longward of what your eye detects, 1 out of every 10 photons makes it to us. So in the infrared, we can actually see. So this experiment is designed or takes advantage of advances in infrared technology. And 25 years ago, there were tremendous advances being made in the ability to use infrared detectors. So I have to say, while people often point to the fact that it's Keck, it's actually the combination of Keck, high resolution imaging, and the tremendous advances that were being made in infrared technology, primarily driven by the aerospace industry. Because of course, if you want to do night vision, infrared technology is the key. So at this point, roughly 25 years ago, we finally got to the point where the detectors were good enough to actually detect signals that were consistent with what we could see at the center of the galaxy with the techniques that we were going to use in the beginning. And our objective was to see how stars move. And the idea is that stars move under the influence of gravity. The closer you are to the center of the galaxy, the faster you move because this force of gravity is stronger. And at the early times, you know, our job was just to prove that we could actually see these stars that are sufficiently close, because remember, you want to show that there's a large amount of mass inside the Schwarzschild radius. So in fact, at the beginning, I really wanted access to Keck because Keck allows you to not only see very faint things, but allows you, because of its size, to see a lot of detail. So the larger your telescope, in principle, the finer detail that you can see. So that was an aspect of these telescopes that was particularly attractive to me. Now, while I realize many of you have already heard about Keck, I want to make sure that I introduce Keck adequately for those of you who haven't. Keck is an amazing facility. It's absolutely why I came to the University of California, because I wanted more than anything else to be able to work with these facilities. These are located on the island of Hawaii, up on the top of Mauna Kea. And Mauna Kea is absolutely one of the best places in the world to do astronomy for a whole variety of reasons. It's because it's isolated. The ocean is around it, so the flow is what we call very laminar. So you have good seeing, you have many clear nights, and there's a host of other reasons. But what I want to focus on here today is that in spite of the fact that you have a very clear view of the center, the seeing is very good, you still have to contend with the Earth's atmosphere. So the photons, the light packets that come from the center of the galaxy, have been traveling to us for roughly 26,000 years. And in the last 30 microseconds, they hit the top of the atmosphere. And when they do that, the light becomes distorted. And this animation really shows you this dramatically. If there was no atmosphere, each of the 5 bright stars that we're looking at here would be the size of the smallest structures you see dancing around here, and absolutely rock solid. So it's the atmosphere, which is great for us. It allows us to survive here on Earth, but it's a total headache for doing astrophysics. So a lot of the work that I've done has been focused on how do we overcome this distorting effect of the Earth's atmosphere. Now, we have many ways that we've come up with doing so. One is Hubble Space Telescope. So we already looked at a picture from Hubble. Hubble overcomes the distorting effects of the Earth's atmosphere by getting above it. But in fact, Hubble, while it's a wonderful facility and has done a tremendous amount of fabulous science, the diameter of the telescope is only 2.4 meters, and Keck is 10 meters. And the kind of science that I'm going to talk to you about today, doing the center of the galaxy, the benefit of getting to a larger telescope goes as the diameter of your telescope to the 4th power. So that's 4 times 4 times 4 times 4. So that's a factor of more than 100. So if you want to get to the highest resolution, then really getting to the highest resolution here is essential. So to do this, what we did is to modify an existing instrument. And this is a picture with the instrument actually out of the telescope. So we had the advantage of not having to start from scratch, but being able to modify the electronics. So a key thing was how fast you read out these instruments, because you need to be able to keep up with the ever-changing atmosphere. So you have to be able to read out very quickly. And you need your pixel scale to be small enough to capture the scale of information that you're after. So the instrument was not designed to do this. We had to magnify the scale that we were using. So it's optics and a little bit of electronics that was required. And I have to say, this is also one of the speaks to one of the real strengths of Keck Observatory, which is the willingness to collaborate and allow their instrumentation to be changed. So I think this is part of what comes from being a university facility rather than a national facility, where it would be much harder to make such changes. So I'm really grateful for that. And since that time, and I would say that these early techniques were rather simple. So they were simple, they were quick, they let us get going, but the long-term objective was to really get to this point of using adaptive optics, which is what's shown here, where we can use lasers and with a much more sophistication, although much more expense, get to the diffraction limit in a more powerful way. So the first decade of our observations were made with this simple, low budget, do what you have to do to just get the this single science project done, while working with a much larger team to achieve a kind of instrument that would be beneficial for the whole community. With this technology, which is called adaptive optics, we can get much higher resolution images, as I mentioned a moment ago, and this gives you a sense of the scale. So if you don't do any of your tricks, those 5 bright stars look like big fuzzy blobs. If you clean it up and try to understand what's going on with the atmosphere, you can actually see the stars that are located at the heart of the galaxy. And it's the motion of these objects that were the focus of this experiment. And while today, 25 years later, this seems so obvious, I have to share with you that the first telescope proposals that we put in for Keck were actually turned down because they didn't believe that our technology would work. And even if it did, they said we wouldn't see any stars, nor would we see them move. So it's really, I think, helpful to remind ourselves what the state of knowledge was just a mere 25 years ago, and how much we've advanced and overcome to get to the point that we are today. Okay, so the original experiment was really just to take images and watch them move. But today, we not only can see them move on little short arcs, which is all we thought we could do in the beginning, but we're actually at a point where we can see them make complete orbits. This is with complete orbits introduces not only much more powerful ways of convincing ourselves that there is a supermassive black hole, but much more powerful ways for actually studying the properties of the black hole itself and the gravity associated with the black hole. Okay, so there are a lot of stars. I'm highlighting one, which is my favorite star in the universe. Its name is SO2. Actually, the fact that it's named SO2 means that we didn't recognize that it was the closest one to the center of the galaxy in the beginning. In the beginning of this project, which is about to flash now, SO1 actually was closer to where we thought the center of the galaxy was. So we thought it was SO1 that was going to win the race. But in fact, SO2 has emerged as the most powerful star. Now, why is it most powerful? It's most powerful because of the stars that we can measure well today, it's got the shortest orbital period. And this is actually, again, remarkable. We did not anticipate this 25 years ago. The orbit of the star is a mere 16 years long. 16 years, that's shorter than a human lifetime. And again, this is not what was anticipated. We were anticipating stars that had hundreds of year periods. So the idea that you actually have something that you could go beyond the statistical measure was super important at that time. Once you have this orbit, it's actually wonderfully simple. And I love this because you can bring it into any introductory astronomy and astrophysics class or any physics class, because it's just back to the basic laws of physics. You can measure the period, how big the period is, how big the orbit is, and that gives you a mass. So that allows you to show that, figure out the mass. Before the experiment started, we knew that there was 4 million times the mass of the sun inside this big circle. And with this experiment, we've actually shown that there's actually 4 million times the mass of the sun in a volume that's 10 million times smaller than this initial volume. In other words, we've advanced the case for the existence of supermassive black holes by a factor of 10 million. And that's a tremendous advancement. I mean, in science, we're often eking out and thrilled about factors of 2. And in this case, we've been able to, over 25 years. So we didn't do this at all in one fell swoop. There were many steps forward, but over 25 years, we've gotten this factor of 10 million. So we've shown that there's 4 million times the mass of the sun inside a region that corresponds to the size of the universe. Sorry, the size of the solar system. All right, now what? Now what next? Once you've gotten to this point, there's all sorts of opportunities. And I have to say, this is one of the wonderful things about working on this experiment, is that at every stage, we keep recognizing how exciting the future is. So rather than getting to a point where we feel like, oh, we do feel like we've closed that chapter, but there's a vast chapter that or door that is opening up to get us to the next step. So the minute we understood that the orbital periods would be shorter than a human lifetime or shorter than a research lifetime, we realized that we could start to test how gravity, the laws of gravity or general relativity, which is our best model for how gravity works near a black hole. And in fact, there have been so far pretty much no tests of how gravity works. There have been no tests, direct tests of how gravity works near a supermassive black hole. So these orbits provide us with the first opportunity to probe how gravity works in this region. And there's actually a number of tests, and I'm going to focus on 2 here, that can be done with these orbits. The first is understanding how photons, the property of the photons themselves, are affected as they travel from the center of the galaxy through the curvature of space-time to us. So we get a phenomena that's called the relativistic redshift. So as the photon moves from the object itself through space-time to the observatory, the photon is actually affected very dramatically when it's near the black hole. So we can compare how photons appear at the extreme of the orbit compared to how they appear close in. Now we have to account for the regular motion, which is how we find planets, the Doppler effect, which you just get from the orbit. But what we're looking for is the term on top of this, the term that comes from shifting how these, the wavelength of these photons, as they have to lose energy because they're climbing out of the gravitational potential. Okay, so that was the relativistic redshift, and that's best measured at closest approach. So you're kind of in business once you, for this measurement, once you've made the measurement of the object all the way around, because you need to know the shape of the orbit. You can't just take a measurement at closest approach and understand this, but you have to go all the way around. So it's the second time you've gone through this, which tells you that it's a 16 plus experiment, 16-year plus experiment. Closest approach was in 2018 for many, many years. Some of you may have heard me talk about 2018, that we were 2018 or bust. So 2018 was a really exciting year for us to actually make this first test of how gravity works. And then I'll come back to the next one. So in after 2018, so this is actually the impact on the y-axis is how gravity has changed the appearance of the photon, or the velocity, apparent velocity, on top of what you expect from just Newton's law. And you see this beautiful deviation on top. So this is about 200 kilometers per second, and it was the first direct measurement using around a supermassive black hole. So that was one of our most recent achievements. And the next goal for our team is to understand how the object itself moves through space. And this is as you would measure through something called the precession of the periapse. And what this is saying is that the object itself is being affected by the strength of gravity. And effectively, what happens is that the object overshoots because of the effect. I mean, you can schematically think of this as the gravity being slightly stronger than you would expect at closest approach, which causes it to come do the spirograph pattern. And this effect is most strongly measured at the furthest approach, because that shift is largest. So we're on that ride up the curve again, because again, like the redshift, you need to have measured a whole orbit. And once you get to the second furthest approach, you're in business. And I have to say right now, we're at the stage where, signals are emerging, but they haven't achieved enough significance for us to publish, but we're in that very exciting discovery regime. Now, other areas that have been super exciting for us is understanding the environment around the black hole, because today, unlike 25 years ago, we used to think, well, which came first, the black hole or the galaxy? It was sort of like a chicken or the egg question. And today we realize that that's the wrong question entirely, because it seems that whatever formed the black hole formed the galaxy, because there's a very tight connection between the mass of the black hole and the mass of the central part of the galaxy. To have this relationship exist, there has to be some feedback between the center of the galaxy and actually, I'm going to skip forward here because I want to leave you guys a little bit of time to ask some questions. And I'll just stay here. So again, there's been tremendous discovery here. I would say the quickest way to say this that is almost every prediction that one can make for what one should see at the center of the galaxy has been inconsistent with our observations. And the three things I'll focus on here is that the predictions are, one, old stars that have been around should congregate near the center of the galaxy. It's like the black hole is the life of the party. So they're not socially distanced. So those are the orange stars. Those are the old stars. And what's striking here is that there are very few orange stars. So while you predict an excess, we're actually seeing a dearth. That's prediction number one. Prediction number 2 is that the gravitational field of the black hole is so strong that it should disrupt the fragile clouds that are the seeds for young stars. So you expect that there should be no young stars. And the young stars in this are color-coded aqua blue. And that's the dominant thing that you see in this animation. The animation being the three sort of the orbits that we've measured, or our estimates of the orbits. At larger distance, they become longer. So these are now only estimates as opposed to having gone all the way around. And there's an excess of them because you expect none. You'll notice that at this point, you also see that there's a uniformity about the young stars. There's a plane of young stars as well, which has been an important clue. And then there's a class of stars that we didn't even think to make predictions about because it was so far from the realm of our thinking that we just weren't thinking about them. And these are the Magenta Stars. And today, these are objects that appear to be tidally interacting with the black hole. So these are stars that when they go through closest approach, the outer envelope is being stretched in a way that we can see. So these are actually the first examples of tidally distorted stars that have ever been imaged in the universe. So this is another recent result of these kinds of observations. And today I find these objects particularly intriguing because I think they're actually are connectors to what are being seen with LIGO, the gravitational wave experiment. Because one of the phenomena that once you start thinking about this, we realize that most stars in the universe are formed as binary stars, not single stars. And if you put a binary star near a black hole, one of the things that the black hole can do is to drive these binary stars to merge and merge much more rapidly than they would otherwise. And when they merge, they actually puff up. And when they puff up, that means that they're big enough because these stars to interact have to be 100 times larger than any of the predicted stars would be. So now we have a mechanism that would naturally puff up a star and leave them puffed up for a long enough time that it wouldn't be surprising to see a star as it makes a closest approach become distorted. So this is one of the many, many surprises that we've seen that has given us lots of fodder for work. So one of the little things I'm now discovering about online things is that usually I can skip ahead without you guys realizing it. So let me just end because I can see that I am a little out of time with, this is a project, as you can kind of see on my left-hand side here, that I'm super excited about for the future of the 30-meter telescope, because that will revolutionize how we see the center of the galaxy. Today, we're just seeing the tip of the iceberg in these animations. You cannot see a typical star. We only see the brightest, most unusual things at the center of the galaxy. And while they're teaching us a tremendous amount, it isn't the bulk of the population. So this is a future that we're excited about, but there's a long way to go from where we are to where this telescope begins. And a lot of this is in advancing our techniques for adaptive optics. So that is what we're going to focus on between now and then, is advancing how we see ever more clearly with the existing telescopes that allow us to mitigate the technological risks associated with this long-term telescope. Now, I do want to just say that all of this has been done with a wonderful team of students and postdocs and collaborators. It's a team that started off as 3 people. Today, we're a collaboration of 30, core collaboration of 30, and an extended network of roughly 100 people. So all of this work involves many, many people. And the students who work with us get trained to do many things, not just to go on in astronomy and astrophysics, but to go off and work in the financial industry. I can explain that connection. That's a lot of fun. The military, and all sorts of other fields. And in particular, these days, big data analytics, because our data sets are large and complex, and our students are incredibly well trained to think about that. So let me just end once again with this animation to say that it has been nothing short of a just a pleasure and a privilege to work on this project. I feel very fortunate to have had the opportunity to be part of the Keck community and the UCO observatories community. It's a really close-knit and highly collaborative community that allows, it's a situation where you really can see that the whole is greater than the sum of the parts. So thank you for your attention.
Thank you so much, Andrea. I know that you wanted to leave a few minutes for questions, so I thought that I would share a few from the chat here. Ed Kemper asked, here's a big old black hole with few stars that seem to be orbiting around it. I assume that he's talking about the illustration we just saw. But how is it demonstrated that the other 100 billion stars of the galaxy see this black hole? Is a dynamical center of gravity for all of them orbit around?
That's a great question. So there's something that's known as the black hole sphere of influence. And that's the distance out to which the mass inside that radius is the black hole plus a mass that's equal to the mass of the black hole. And outside that radius, it's assumed that really, because each star is influenced primarily by what's inside it. So beyond that radius, the black hole is really just one of a lot of other stuff. So the black hole dominates the motion of things that are really at the heart of the galaxy. And beyond that, it's dominated by the cluster plus the black hole and so on and so forth. So it is true that you could remove the black hole from the collection of objects at the center of the galaxy and the sun wouldn't care.
Ronan asked about the Magenta Stars. What would an observer on a planet of one of the Magenta Stars see at closest approach? Are there any relativistic effects that would be material? For example, meaningful time dilation?
Okay, so I think there's two questions in there because what would you see on, I think, because the planet around a star, if you were on a, actually, let's go, let me take that question at face value. If you were on a planet by a magenta star, you picked the wrong star. Because those are stars where the black hole is pulling off material. So depending how far out, that material is going to start to interact with your planet. So that's going to be one of the issues. The other issue is that as you get, just in general, for planets going around these stars, is that as you approach the black hole, if you're not really close to the star, the planets will be ripped off for the same reason that these bloated stars are losing their atmosphere. So a planet would have the same problem, which is it would start to be disassociated from the star and then just start orbiting the black hole rather than the star. So a typical, like the sun around, the Earth around the sun couldn't survive at the center of the galaxy on SO2's orbit.
Alec asked, so there really is a true actual quote unquote singularity inside each black hole. Such physical object being infinitely dense and infinitesimally small and yet still having only a finite mass and coming into being in finite time. Has this been directly verified?
So this project provides the best evidence to date for black hole, supermassive black holes. And as you can see, it's a density argument. It's really showing that there's mass inside a small volume. If you were being a true skeptic, there's still wiggle room. In other words, the radius that we've confined the mass to, for the mass of this black hole, is 500 times larger than the Schwarzschild radius. But it is by orders of magnitude better than anything that's out there for supermassive black holes.
Great. Prashant asked, how do you determine what's at the center of our galaxy? That's where we started this whole talk.
So that's a great question. And as astronomers and astrophysicists, or whatever you want to call us, that's It's an indirect science. So what are our opportunities? So traditionally, we can take pictures. And what's nice about this work is that we're sufficiently close to the black hole that now we can actually measure the motion. So we can actually use gravity as the understanding of what's there. Because only tracing what emits light often misses a bunch of what else might be there. And in fact, I would have to say that this is one of the emerging, for me, one of the most exciting things for us to pursue in the coming years is truly understanding what's underneath the waterline. So as I said today, the images let us see the light from what's the tip of the iceberg, the brightest thing. But in fact, what may be dominating the mass of what surrounds the black hole may not be luminous. And these orbits actually can probe that non-luminous contribution. And in fact, the way it would show its signal is by, again, measuring the orbits of stars. And unlike gravity, Einstein's version of gravity, that makes which has a prediction that the orbit should precess, an extended mass should make those orbits open up, or either go less slowly in that direction or open up entirely so that you're actually going the other direction. So I have to say, this is actually one of the things I'm most excited about pursuing now, is really understanding whether or not we have the capacity to probe that extended mass distribution.
We've gone a few minutes over, but if you have a few minutes more, I've got just two last questions for you. As I'm sure you're used to getting this question, we all want to know, is this thing feeding? And also, I thought a really interesting question: how do you remain patient when you know it's going to take 25 years to find your answer?
Well, let me start with the second one first. We didn't know it was going to take 25 years because we didn't even think about measuring orbits. We were only thinking, we proposed this. So when I first put in the proposal, it was a 3-year project, because all I thought I could do was measure velocities, speeds on the plane of the sky. Because remember, people didn't even believe that we could take an image, never mind 2 images that showed something was not at the same place. So in some sense, the patience has been born out of a lack of understanding of the long term. So you start off with 3 years, and then you think you're going to get an acceleration, which is just a little bit further. So it's almost like just understand, you set your goals to be something that is reachable within a reasonable amount of time. And this project has been so rich with scientific discovery. I mean, I've only tried here to give you a sense of the discovery and the different regimes. Maybe now I've almost forgotten what the question was, but let me give you a sense. Because I think it had something to do with the black hole feeding. And this gives you another sense of just the wide variety of projects and collaborations that have come out from this. So we do actually see emission from the black hole. And we associate that with the feeding of the black hole, just like in the AGN, which is much more luminous by orders of magnitude. So this is just wimpy little stuff that presumably is like the black hole snacking. And we've been trying to understand that process, both in terms of the source of the matter that's feeding the black hole, and also the state of the material or the plasma that's there. And it's variable, it's highly variable. So on the left, you see how bright it is as a function of very short time scales. And so we've actually collaborated with a finance professor to model these kinds of variations, because one of the things that we know from finance is that if you study the variation in the market, you can see different things emerging. And at the time that we were doing this project, it was right before one of these bloated stars passed through closest approach. And there was a huge controversy at the time about what they were. And one hypothesis would lead you to one idea was that there was a lot of material that was going to fall onto the black hole, and the black hole was going to light up. Well, the black hole is varying all the time. So how do you know that something's changed? So what we wanted to do was come up with a tool that showed that there was a change in the state, a second state, which is what finance, because of course we all want to know what the state of the market is, showed. So hopefully that answers two questions, both parts of your question, which is we can see the black hole. We see it directly. We see it all the time. And we didn't see it at first with this, the first 10 years technique, which was simple. It was only the second year, the regime that we're in now with adaptive optics, which is powerful enough that lets us see much further down in terms of the water line and what's there. So we see it all the time, and it's varying like crazy. So there's a whole branch in my group that's focused just on understanding the accretion physics, or the growth of the black hole through a lot of different means. So I guess it's just 25 years. It's just been so exciting. Why would you want to do anything else? I mean, we have this privileged position of being able to set our own research directions, and the fact that we have long-term goals as well as short-term goals that can be teased out of this 25-year data set, I think also helps us sustain both our interest and the data set. It's a non-negligible problem for how do you keep a data set and a code base alive for 25 years. That exceeds the typical lifetime of a grad student. So we actually have some, at this point in the project, we have some interesting infrastructure challenges that we have to think about for getting to our next scientific goal. I think you're muted.
Thank you. I'm just going to share again as a reminder to everyone. Thank you again so much, Andrea, for joining us tonight. It's a pleasure and a privilege to work with you and to hear directly from you and this talk. I just so much appreciate your time. For those of you joining us, we hope that you will join us again next Monday at 4 p.m. If you are keeping track, we typically go back and forth between the living room lectures and the Ask an Astronomer. If you enjoyed this last part even more than the first part, where you got to ask questions, Ask an Astronomer's for you. Next Monday at 4 p.m., Dr. Alex Filipenko will be joining us from Berkeley and answering your questions. You can submit those online on our social media at Facebook, UC Observatories, Twitter, Instagram for Lick Observatory, and Facebook there as well. Or you can reach out directly to social@ucolick.org for more information about these upcoming events or to submit your questions in advance. We typically spend about half an hour at the Ask an Astronomer series. So please join us at 4 p.m. and have your questions ready. In the meantime, let's all give Andrea a round of applause from whichever living room that you are joining us from. Thank you so much again. Hope that you all have a wonderful week.